for those who are not here, we did a derivation with initialization example, derivation 2 with iteration example. Now we're doing derivation 3 with theory and failures. So the two theory things which we are trying to tell is that the choice of x cube plus ensures or making x cube plus greater than 0 ensures objective function value decreases. This is the very first choice which you make in your simplex, that you make the q from the mu n's which are negative, pick one of the q's and make the corresponding x cube plus greater than 0. What it does not ensure is that in the next step after the swapping of indices, your mu's may stay negative, but your objective function value will reduce. So we're going to prove this. So to do that, let's write the C transpose x plus in terms of C transpose x. If I can show that C transpose x plus is less than C transpose x, then I'm done, because this is my objective function value. That is where we are going. So let's write it down. So we'll split it into components. So we'll write it as a B component, C transpose B times xb plus Cn transpose xn plus. Now what should I do? Getting too tiring for me. Getting longer and longer. Okay, so what should I do now? Is this equal to 0? Is xn plus equal to 0? Athar? Yeah, no. Right. What's your name? I'm just checking, Vedant, why it's not equal to 0?
Because after selecting one.
Because we are making one index greater than 0, no? So we are separating this like we did in the proof when we proved it. So this remains CB transpose XB plus Cn complement the Q transpose Xn complement the Q plus CQ times XQ plus, sorry, because we are making XQ plus to be greater than 0, so we have to separate it out. Now this guy is equal to 0, right Vedant? Alright, we'll do some more substitution. What was XB plus? What was XB plus? Look up your simplex. XB minus B inverse AQ XQ plus CQ XQ plus. Correct? This was XB plus which we derived. Remember, by making AX equal to AX plus, we got this as XB plus. Correct? So I just substituted it. Now what we'll do, expand this a little bit. CB transpose XB minus CB transpose B inverse AQ XQ plus CQ XQ plus. I'm going to work on this element component now. Okay. So recall let's take this component, write it down, CB transpose B inverse AQ XQ plus. Now help me simplify this. What is CB transpose B inverse? Correct? Who said? Lambda transpose. What was lambda? Lambda was B inverse transpose times CB. So we are writing as CB transpose B inverse. So this is lambda transpose. Huh? So this is lambda transpose AQ times XQ plus. Now you have to tell me what is this guy. Recall your KKT conditions, the Lagrange multiplier condition. What was that? The Lagrange multiplier. I know this is a little intensive, that's why I'm doing it in breaks. What was the Lagrange multiplier condition? C is equal to A transpose lambda plus mu. But here we don't have A, we have AQ. So what will we do? We'll take the component of that. So what we'll do is, so you recall your KKT, like Sanjana just said, C is equal to A transpose lambda plus mu. Correct? And this will have all the components of that. Correct? The components of C, the components of mu, and the columns of A times lambda. Correct? Now I want to pick only the qth element of this. So I can write it. Remember, we had split it into CB and CN. We had written CB is equal to B transpose lambda plus mu B, CN is equal to N transpose lambda plus mu N. Remember that? So which means that you can separate component wise. So I'm going to pick one component of this and I'll write it as CQ is equal to AQ transpose lambda plus mu Q. इसमें से जो qth रो आ रही होगी ना, उसको लिखा है मैंने. I've written the qth row out of this set of rows. Everybody with me? If q was 2, I've written the second row of this expression or equality. So now what is A transpose? AQ transpose lambda is CQ minus mu Q. What is lambda transpose AQ, which we need? Do you need a transpose? These are scalars. These are just one value. This is one element of C and one element of mu. So if I do the transpose, it doesn't matter. Everybody with me? So I'm going to take this guy and put it in this. So my hash becomes CQ minus mu Q times XQ plus. Everybody with me? Now I'm going to take the hash and substitute back into my main expression. So your C transpose X plus is equal to CB transpose XB, and instead of hash I'm going to write this. Is that okay? So minus CQ minus mu Q XQ plus, and then this element plus CQ XQ plus. Correct? Connect? You here? You're unhappy? Okay. Alright. Alright. So now CQ and XQ plus will cancel out. Correct? So this is CB transpose XB plus mu q xq plus. And now we are done. Now somebody tell me why I am done. Correct. So what I could write this as CB transpose XB plus CN transpose XN plus mu q times XQ plus. Why? Because this is anyway 0. So this is nothing but C transpose X plus mu q XQ plus. What is this? Negative. What is this? Positive, which means that the whole thing is negative, which means that this is less than C transpose X. Can everybody see? So just by making XQ plus to be strictly greater than 0, we are ensuring that the objective function value at the next iterate becomes lesser than the objective function value at the previous iterate. Everybody okay? Okay, so that's one proof. The last proof which we wanted to do okay, the last proof is the non-singularity of B, and in the past whenever I have taught, sometimes I've skipped it, sometimes I've done it, but in the past 2-3 years I've started doing it because I've started doing it with an example. If I do it in the general case, you get confused. So first I'll do an example, then we'll do it a general case. Okay. So the question was, by the swap which we do, does the new B matrix stay non-singular? This is the question which we have not answered yet. So let's do with an example. So I'll take the example which I was following in the when I derived it. 1, 3, 5, and then let's say the n was 2, 4, and then after this, so we swap these two, let's say. So this is your P and this is your Q. So P is 1 and Q is 2 of the overall set, which means that your new B, which will come out as 2, 3 and 4, and your new N will turn out to be 1, 4. Okay. So to this new B, although in the derivation I didn't refer to as plus, but this is mapping to the X plus. This is the B plus set after the swap. So let's say I write B matrix times this. So this is the B plus set. Remember, once we swap, then we initialize again. So technically we never work with B plus or N plus because they become the new B and N or the initialization state. But for the sake of argument, I am referring to this B plus. So the corresponding B matrix is B plus, let's say. So now what I'll do is, let's say I write B inverse times B plus times E2. What is E2? E2 is the second canonical vector. What is a canonical vector? It is the column of the identity matrix. I'll tell you in a minute. So what I did was, this is B plus, index set B plus, this is the matrix B plus. So if I do B inverse B plus times E2, E2 is the canonical vector where on the second place it's a 1 and the remaining places are 0. It's, since I'm working with R is equal to 3, so that's why it's 3-dimensional, and for the moment. If it is R-dimensional and I'm doing E2, that the second place it will be 1 and all the other positions in the vector will be 0. So, okay, so we wrote this. Now, what is this? This is equal to, this is a vector, है ना? These are the second column of A, third column of A and the fifth column of A, because B plus matrix contains A2, A3 and A4. Sorry, 2, 3, 5. So it is the second, third and the fifth columns of the A matrix, correct? So that is why I am writing as A2, A3 and A5. So what will be the product of this times this? It will be B inverse A3. Everybody agrees? Okay, so what I'll do, I'll write this as B inverse A1, A3, A5, 0, 1, 0. Is there anything wrong in this? Is there anything wrong? You multiply the second row, it will get the first row. A1 times 0, A3 times 1 and A5 times 0. What is this now? What is it? It's B, right? So, E2. So basically if you do B minus B plus E2, you will just get E2 if it is not the column which you are swapping, the column which you are not touching, correct? Here we have taken Q to be, we have taken it to be we are swapping the first column. So when we are doing E2, we will get back E2. When I do B minus B plus E3, what will I get? We'll get E3, right? Because it's the same argument will happen. But when I will do B inverse times B plus times E1, then what happens? So this will be B inverse. What is B plus? B plus is again A2, A3 and A5. It is the matrix after the swap. A3, A5, and it is 1, 0, 0. Correct? So we get as B inverse A2, which is nothing but B inverse AQ. What was Q? Q was 2. So it's the second column. What is this from your algorithm? D, correct? Everybody agrees? So this is D. So now we'll put the whole thing together. Why I have done this will be clear in a minute. So if I have to write B inverse B plus E1, B inverse B plus E2, B inverse B plus E3, and I put that in a matrix format. This is B inverse B plus E1, E2, E3. What is E1, E2, E3? Identity matrix, right? It's 1, 0, 0, 0, 1, 0, 0, 0, 1. Correct? Everybody? So this is nothing but B inverse B plus. This is what we know standalone. Now using this, this and this, what do I get? This is using this, I get, what do I get? What is B inverse B plus E1? B. What is B inverse B plus E2? What is B inverse B plus E3? Everybody with me till this part? Okay. So now look at this matrix. So in this, how many elements we have? R is 3, right? So we have D1, D2, D3, 0, 1, 0, 0, 0, 1. Correct? Okay. To prove that B plus is invertible or non-singular, what do I have to prove? We have to prove that this thing is invertible. Why? Because B plus is B times this matrix. Product of invertible matrices is invertible. So if I can prove this matrix which I am showing to you is invertible, then I am done. Everybody agrees? Okay. Let's be more explicit. What should I erase? I'll keep this, hai na? I'll erase this because you've seen this. Okay. So now let's look at this matrix. What do we know about D1, D2 and D3? So what do we have to show? D1, D2, D3, 0, 1, 0, 0, 0, 1 is invertible or non-singular. Correct? Do we know anything about D1, D2, D3? Yes, Sanjana. Yeah. Which one is greater than 0? All cannot be greater than 0. They can be, right? So, like Sanjana said, we know that D1 is greater than 0. Why do we know? Because P is equal to 1. P is equal to 1 was chosen because it was the minimizing index of minimized xbi divided by di. Remember? Correct? Yes or no? So we know. Look, I'm so tired, my writing is going all here. So we know that D1 is strictly greater than 0 because P is equal to 1. It was the swapping index from the B which you are picking and kicking out. Remember? Minimize I, di greater than 0, xbi divided by di. Now let's look at this matrix again. So this is greater than 0. I don't know anything about D2 and D3 and I don't care. 0, 1, 0, 0, 0, 1. Is this matrix invertible? Yes, because it's a set of linearly independent vectors. Why are they linearly independent? Let's try to argue for that. What does linearly independence means? That if you write them as a linear combination, all the constant will be equal to 0, or one cannot be written as the sum of the others. So first of all, these two are linearly independent. You cannot be, because they are canonical vectors. Anyways, they are linearly independent. So don't have to worry about them. When you look at this guy and this guy, can you write this one in terms of the other? No, because anything which you try to multiply with this will become 0 here, which you can't do. Same thing, this and this cannot be written as a linear combination of each other. So we did the individuals. Now you do the twos together. So can this and this together give you this? No, because you'll have to multiply with something 0, otherwise this will not come out to be 0, and the linear combination says it should be non-zero constant when you do a linear combination. Same thing when you do a combination of this and this, you can't get this. And if you do a linear combination of this and this, you can't get this because they are positive all on different indices. I mean, that's the simplest way of saying, but you can be more elaborate and write it down that you can't write linear one in terms of the other, or you combine any two and you can't get the third. So that is how you can argue. Which means that this matrix is invertible, which means that B plus is invertible. Is that okay? You can do that also. You can find the determinant and you can say determinant is non-zero, so it's. I mean, I usually stick to linear independence because that's, I think, is more intuitive. But you can compute the determinant, right? So what will be the determinant? D1, right? Yeah. So the determinant will be non-zero, so you're done with that. Should I do the general case or it's okay now? So you can do this now general. So I'll just write it down just because I'm completing, let me complete it. Any doubts on this? So once you go back and read the notes, because I've given you too much information today. I know 2 lectures together is, and we have exceeded 2 actually. So we have done more than 2 lectures. So I know that's too much information. But once you go and read it, and now the recording is also there, so you can see the recording. I'm sure it will be clear to you. I don't know what will happen those who are not there. So because it's a difficult topic, I would have wanted them to come. So now let's write the general form, है ना? So in general, generalize as B inverse B plus is equal to E1 till Em minus 1 D Em plus 1 through Er. So this is the mth position. This is the mth position in the B set, which is corresponding to Q in overall set, where P will come. So now you can do this, and then you can show that. So this will be 1 0 0 0 1, and there will be 0 0 0 Di, or whatever D's will be there. This will be greater than 0, it will be 0 0 0 1. So this will be the Pth position. And this is the Qth position. This is the Qth position. So in general, it will turn out to be this. This is the place where you would be doing the swapping. So you would know that this will be greater than 0. And then with the same argument, you can show that all these vectors will be linearly independent and hence true. Everybody okay? I'm not going to give this in the exam, so don't worry. But I wanted you to at least know the whole thing, so that you know where the simplex is coming from. Okay, so we'll stop here, and then you come to the lab and then code it up. And you had also asked me to go over more real life examples, so I'll pick 3 more papers this time, and we'll go over them as well. You can stop. Okay, so see you in the lab.